Hello, my name is Arpit Mishra, and I'm going to be going through my topics 5 through 12, solutions and concepts that I achieve in them. So for problem number one, I have an outdoor fountain, and it has like many parts to it. And so there's a water fountain that flows into a little reservoir that then goes through marble tubing, and which then drips into a reservoir, and then that reservoir is connected to a pump, which pumps it all the way back up into the water fountain. So in this case, I'm covering topics 5, 6, 7, and 8. And those are internal fluid flow, pump analysis, flow through porous media, and external fluid flow. So for the first part, the first question, I ask to give the friction loss for the problem. And so I ask to show the Reynolds number. Here's all my knowns. Here's my what you have to find, and here's my assumptions. So I assume steady flow, no additional forces do anything on this piping part here. So here's my picture, and so the solution is, this is how you would start it. So you'd have to solve for the Reynolds number. You'd get a Reynolds number, and then from the Reynolds number, I calculated what the laminar fanning friction factor would be and what the turbulent fanning friction factor would be. And so the laminar one is incorrect, so we wouldn't use it in this case, and therefore we're using the turbulent fanning friction factor. Then from the fanning friction factor, we can figure out the friction loss with this equation here, which you can use for laminar or any turbulent at any angle. And after plugging some values in, we get a energy per unit mass solution. Then for part two of this question of the fountain, I say, using the information from the previous part here and list all my known things I know, I ask to find the max height, which would be delta Z in this picture here, the pump can be placed at. And so I said assume to ignore all the friction and losses, including the stuff from part one, so we don't get that mixed up. So in order to determine delta Z, we have to figure out the friction loss through this turn here. So we figure out what it is here, and then we use the equation for NPSHR, and then it's right here, and then we rearrange it and we solve for P. And then after we do that, then we can do the Bernoulli's equation from point 1 to point 2. And then we are able to cancel out many terms, such as the pressures, and rewrite them. And then the first velocity, it's at 0 at this state down here, and then it speeds up. So there's that. And then we solve for the friction. So then rearranging, we can solve for delta Z and then plug some values in. And I ended up getting a value of negative 1.61 meters. And basically this just meant that the pump had to be placed underneath the reservoir, if you think about it in that way. And then for the next part, I say, assuming like the water trickles through this little catching part here through little marble tubing and into a reservoir, I ask to determine the superficial velocity and the permeability of the marble bed. So here's all my knowns, which is everything from parts 1 and 2. I give the diameter, etc., for the marbles. So then we solve here for the friction, and then we once again use Bernoulli's equation. And a huge part I forgot to mention was that since it is trickling water, we can assume it's laminar. And since it is laminar, we're able to use Darcy's law. Otherwise, we would not be able to. So doing this, we solve for the friction loss. And then we're able to solve for the superficial velocity using this equation here, plug some values in, and we get the superficial velocity to be this value. And then after that, I asked to determine the permeability of the bed. And once again, this is because it is laminar. We're able to do this, plug some values into this, and we get a value in Darcy's. And then for part 4 of this problem, I say after a few days, your water fountain basically clogs and there's like overflow through your reservoir. And you being curious, you basically want to figure out what the terminal velocity of a marble would be if you just dropped it in there. So I say you can start from the terminal velocity equation that was derived earlier in our class. And we just plug some values in, we get a value of this here for the terminal velocity. And in order to be able to use this coefficient of friction that I've given here, we had to make sure that the Reynolds number was appropriate to use it. And that's why I asked to check the Reynolds number at the end. And here we do that, and it is less than 10 to the 4th power, which means that it's laminar flow. So therefore, the coefficient of drag was able to be used. And then moving on to my next problem, which covers, I believe, topic 9, which is compressible flow. I say that you work for a balloon company. There's a series of adiabatic compressors, and you basically are compressing helium from a room into like their little tanks. And there's a series of 5 compressors that they go through, and there's interstage cooling. And I ask for the work to do the compression per mole. So we have this equation for the work per mole. And then we determine the P ratio, plug that in. And then once we do that, we're just able to plug and chug, and we end up figuring out that the work per mole is this value here. And then for the last problem, I cover topics 10, 11, and 12, which are microscopic masses and momentum balances, which is Navier-Stokes, their boundary conditions, and the analytical and numerical solutions to these. So for this, I did basically like water flow through a pipe from the top of your house to the bottom of your house, and I asked to figure out the analytical and numerical solutions to this. So I give some knowns, which are steady flow, fully developed, constant density, constant viscosity. It's wide and there's no slip at the walls. Here's a cross-sectional view, coordinate system, and the velocity would definitely be fastest here at the bottom, and it would be 0 at the walls because it's no slip. So to begin, we start with the continuity equation, in which we can cancel out some terms, and we Stokes, we end up using the y component since the flow is moving downwards. And then in this, we can cancel out some variables because of continuity, velocities being 0, and we ended up getting this solution here. And then we apply the boundary conditions of which we know at x equals 0, dv dy over x equals 0, so which is the no slip condition at the walls. And then the other one would be if this was the 0 on the coordinate system, then d over 2 in the positive direction and d over 2 in the negative direction would also give velocities of 0. That's symmetrical. So then we integrate once, plug in boundary conditions, integrate it twice, plug in boundary conditions, and we end up getting a final velocity profile in terms of x for this problem. So this is the analytical solution. And then I ask to give the numerical solution, which basically we do the same thing. We just don't integrate yet. We replace the d squared dvy over dx with the appropriate differencing equation. Then we have our boundary conditions, analytical solutions. Then we plug everything into Excel. And after we do that, numerically, we figure out that Vmax should be 54.5 centimeters per second. And following that link that was on the solution sheet, we get to here, which shows how we figured out the answer to the numerical solution.